Okay, students, we're beginning our work on related rates. Here's an example of a related rate problem. The area of a circle increases at a rate of 20 inches squared per minute. At what rate is the radius increasing when the radius is 5 inches? If you ask yourself, what is changing? There are a lot of things that are changing. First of all, it says that the area of the circle increases at a rate of 20 inches squared per minute. That's the rate of change. It's a derivative. And the area, it says, is changing, so we know area is changing. It's wondering what is the rate of the radius. You know the radius is changing. Also, time is changing. And so you can see that we have area, variable A, radius, variable R, and time, variable T, that are all changing. And as those change, it creates an issue for us to be able to try to find the derivative. They are related rates. As one changes, the other changes. So we got to try to make a go at it. In these type of problems, I like to outline them like this. I start with this first box. I like to model the problem. Second box, I like to write formulas, relationships, variables, anything like that. This box, I like to come up with a plan. In this box, I like to solve. This is how I do it. So, we model the problem. The area is increasing. Well, we've got the circle going out, getting bigger. The radius is increasing, just so we understand that's the shape. So what kind of formulas, relationships, variables can we express in this type of problem? Well, you do know that the area is equal to pi r squared. You know that that's the area of a circle. You also know that you're looking for the area prime, the derivative of the area. I'm sorry, you're looking for the rate of the radius. You know that a prime is 20. The area is increasing at a rate of 20 inches squared per minute. You know that the current radius is 5. That says that right at the end of the problem. The question is, what is r prime? Well, we're going to come up with an r prime. This is where I create my plan. We're going to take the derivative with respect to time of area equals pi times r squared. Derivative with respect to time. If I do that, the derivative with respect to time of a equals the derivative with respect to time of pi r squared. What is the derivative with respect to time of a? You guys know, because we've used implicit differentiation to solve these type of problems, we get a prime. Derivative of pi r squared, 2 pi r, r prime. Now that we have that equation, as we've taken the derivative, we can plug in the pieces we know. Area prime, 20. R, 5. R prime, we don't know. 20 equals 2 pi times 5 times r prime. 20 equals 10 pi. R prime. Divide both sides by 10 pi. 20 over 10 pi equals r prime. 2 over pi equals r prime. Let's create a label. The question originally is, at what rate is the radius increasing? Looks like we're in inches and minutes. So r prime equals 2 over pi inches per minute. And that's the answer. So you can see that, you know, this is a lot of work. It does require us to be neat. Keep our work in front of us. Know for sure what we're solving for. This problem I wrote minute at the bottom there. Sorry, it should be second. We'll try another problem. Volume ball is increasing rate of 10 cubic centimeters per second. So obviously we have a volume problem here, a little bit different formula. At what rate is the diameter increasing when the volume is 100? Same thing. I'm going to create my box. There we go. I'm going to model it. I'm going to write my formulas, my variables, relationships, anything like that. Make my plan. I'm going to solve. Model. I got a ball. It's increasing. It's getting bigger. A rate of 10 cubic centimeters per second. It's wondering what rate the diameter is increasing. I'm not focused on the radius this time. I'm looking on the diameter. Looking for the diameter. Well, the first thing I'm going to write down is that the volume is equal to 4 over 3 pi r cubed. That is the volume of a sphere. We're assuming that this ball has a nice spherical shape. Do I know V prime? Yes, it's increasing rate of 10 cubic centimeters per second. Do I know R? Current radius? No. Do I know the current volume? Yeah, it's 100. Do I know the current diameter? No. As you can see here, I'm trying to solve for d prime. It says at what rate is the diameter increasing, but my formula has only r cubed. It has an r in there. So that means I need to set up a relationship, namely that diameter is equal to twice the radius value. If I solve for r, I get r is equal to 1/2 d. I can take that and plug it in. Then I'll have an expression that involves d. And I can hopefully solve for d prime, which is what I'm looking for. Again, I'm looking for d prime. That's why I did that. That's my plan. Take the derivative with respect to time. And I'm going to use the function, or the formula, v is equal to 4 over 3 pi times 1 over 2 d cubed. I'm going to make that look a little nicer. We got v is equal to 4 over 3 pi times 1 over 8 d cubed. We got volume equals 4 over 8 is 1 over 2, so let's go pi over 6 d cubed. There we go. That's my volume. And I want to take the derivative of that. And if I do, I'll come up with a d prime, and I'll be able to solve for d prime. So the derivative with respect to time of the volume is equal to the derivative with respect to time of pi over 6 d to the third power. Derivative of the volume with respect to time is v prime equals 3 pi over 6 d squared d prime. an implicit differentiation because as you look, our variable t does not match up with v. Our variable t does not match up with d, so we have to use that implicit differentiation piece. So I do that, come over to v prime is equal to 3 pi over 6 d squared d prime. Now I can figure this out because I know that v prime, from what we were given up above, is 10. 3 pi over 6 would be pi over 2. But what is d squared? What is d squared? I don't have d, but I do have v. I know the volume is 100, so I'm going to use that. If the volume is 100, I should be able to figure out the diameter. 100 equals pi over 6, d to the third, multiplied by the reciprocal, I'd get 600 over pi equal to d to the third. Cube root both sides. I think 5.76 is what we want. Check my work. Yeah, 5.76 is equal to the current diameter. So the diameter is 5.76. So I can plug that in. Pi over 2 times 5.76 quantity squared times d prime. Solve for that. Multiply by the reciprocal, I get 20 over pi equals 5.76 squared times d prime. Divide by 5.76 squared, and we come up with 1.92 centimeters per second. So you can see the amount of work. It's very nice to keep it organized. I model the problem, formulas, relationships, variables, create a plan, and then go about solving it. Let's go to the next problem. Airplane is traveling east at 600 miles an hour. Another is traveling north at 750. They left the airport at the same time. How fast is the rate of their distance apart increasing after 2 hours? Sometimes you don't even know where to start. So if you want to start by drawing the boxes. Hopefully that will help us out. Model. Formula, variables, relationships, plan, solve. One's heading east at a rate of 600. One's heading north at a rate of 750. The question is, how far apart are they? What's their distance? Rate. How fast is the rate of their distance apart increasing after 2 hours? You got a lot of stuff here. We don't have n and e, we have n prime. We know n prime is equal to 750. The rate at which the north distance is changing is 750. We know east prime is equal to 600. We also know n. If they've been traveling for 2 hours at a rate of 750, then the distance must be 1500. If they've been traveling for 2 hours at a rate of 600, then the east distance must be 1200. And we're solving for d prime. Do we know d? We could figure it out. Do we have to? Well, let's see. What type of relationship could we set up for this? Well, it looks like I have a right triangle, so I could use the Pythagorean theorem here. namely that d squared is equal to e squared plus n squared. So let's do that. Let's plan on taking the derivative with respect to time of d squared equals e squared plus n squared. And you can see that when you take the derivative of this, you're going to come up with a d and a d prime, e and an e prime, n and an n prime. Do I have all those pieces? I have n prime, I have e prime, I have n, I have e. I'm solving for d prime, so that's okay that I don't have that, but I'm going to need d. And just to show you, if you take that derivative, the derivative of d squared is 2d d prime. Derivative of e squared is 2e e prime. Derivative of n squared is 2n n prime. So we are going to have to find d. Well, that's not too hard. D squared is going to be equal to 1500 squared plus 1200 squared. I can use a Pythagorean theorem. Square both sides. Come up with 1920.93. So now we have all of our pieces. Let's plug them in. 2 times 1920.93 times d prime is equal to 2 times e is 1200, e prime is 600, plus 2 times n is 1500, times n prime is 750. And if we combine these terms and then divide it by our 2 times 1920.93, we get d prime is equal to 960.47, and we're in miles per hour. There you go. So again, it doesn't have to be a formula like, a formula for volume or area. Sometimes the Pythagorean theorem comes in very handy with this stuff as well. One last one. Corn is being emptied onto a pile at a rate of 12 cubic feet per minute. It is taking the shape of a cone. How fast is the height of the pile increasing when the pile is 6 feet high and has a base diameter of 8? Again, a lot of people, when they look at these problems, you don't know where to start. And the good thing is if you draw your boxes, at least you know where to start. And after a while, you just know what the boxes mean. I'm going to draw my box. If I do, I'll model it. Variables, relationships, formulas, anything like that goes over there. Make my plan. And solve. Well, let's make it a pile. It's a cone. It says that the current height of the pile is 6 feet. It says the current diameter of the pile is 8. And we're dumping on material at a rate of 12 cubic feet per minute. Cubic. That's a volume piece because it's to the third degree, third dimension, volume. Volume of a cone, I'm sure you all remember, volume is equal to 1 over 3 pi r squared h. We know v prime. V prime is 12. We don't know r prime. We don't know h prime. We know the current radius. The current radius is 4. Diameter is 8, radius is 4. We know the current height. Current height is 6. What are we looking for? We're looking for h prime. What do we have to find in r prime? Well, that's a good question. As you look at this problem, you have r squared times h. That would require the product rule. You guys know 2r times h. I'm sorry. Derivative of r squared would be 2r prime times h plus r squared times h prime. Well, look at that. If we were to do the product rule, we would have an r prime and an h prime. We don't know what r prime is, and we can't solve for those two unknowns. So what we have to do is we have to insert something. Since I'm looking for height, I would like to get rid of this r and replace it with h. Now, how do I do that? Well, if you look here, we have a radius of 4, a height of 6. We have a right triangle, and that pile, as it increases, it's going to create similar triangles all the way up. And so really what I have is 6 is equal to my height, radius is equal to 4. So I can say that the height divided by the radius is equal to 6 over 4, a constant ratio. And I want to solve for r. I want to solve for r. 6r, if we cross multiply, is equal to 4h. Divide both sides by 6. R is equal to 2 over 3h. Looks like I now am good to go. What is my plan? My plan is to take the derivative with respect to time of my volume equals 1 over 3 pi r squared h. Let's get that formula. Volume equals 1 over 3 pi. What is my radius? It is 2 over 3 h 1 squared times h. Work that out a little bit more. Volume equals 1 over 3 pi. 2 over 3 squared is 4 over 9. I have h squared times h. Finally, volume is equal to 4 pi over 27 h to the third. Great, now I've got a volume formula that's strictly in terms of the height. Well, let's solve it. Take the derivative with respect to time of the volume equals the derivative with respect to time. I didn't need those parentheses, I don't know why I did. 4 pi over 27 h to the third. Derivative with respect to time of volume is v prime. Derivative with respect to time of 4 pi 27 h to the third. 3 times 4 pi over 27 h squared times h prime. Do I know h? H is 6. Do I know v? V prime, excuse me. V prime is 12. So 12 equals 3 over 27. That's going to reduce to 1 over 9. So 4 pi over 9. 6 squared is 36 times h prime. Divide both sides by 36. 1 over 3 equals 4 pi over 9 times h prime. Multiply by the reciprocal. 9 over 12 pi equals h prime. 9 over 12 simplifies to 3 over 4. So the height is increasing at a rate of 3 over 4 pi, and we are in feet per minute. Again, as you can see, reading these problems, you often don't know where to start. If you model it, write down your variables and formula, create your plan, and solve. Just start by drawing your 4 boxes. Hopefully you'll have a place where you can get started and start to work these out. They're not easy, but again, hopefully you have a place to start. We'll need to practice this. Good luck. You guys do great.